So we're going to go with question 3.8. Methane gas, initially at 8 megapascals and 300 Kelvin, is heated while maintaining constant pressure in a piston cylinder device until its final volume has increased by 50%. Determine the final temperature using the ideal gas equation of state and the compressibility chart. So let's get the property tables ready. Okay, so we're going to start first by trying to estimate the final temperature using the ideal gas equation. We've done that before. So this is methane at 300 Kelvin and 8 megapascals. We know from the ideal gas equation that P1 V1 over R T1 equals P2 V2 over R T2. Of course, R cancels out since it's the piston cylinder, the pressure isn't changing. So P1 is P2 and that cancels out. And we're left with V1 over T1 equals V2 over T2. Now we're looking for T2. So if we isolate that, we're going to get T1 V2 over V1. We know from the question that V2 over V1 is 1.5, right? Because it's increasing by 50%. The volume. So T2 is equal to 1.5 T1. We know T1 is 300, so 1.5 times 300 gives us T2, 450 Kelvin, okay? Now this is our first estimate, and the reason it's an estimate is because this is the ideal gas equation. It employs certain assumptions and approximations that might not always be valid, and this is why we're going to try again using the compressibility charts and see what we get. So if you'll remember the compressibility charts, we need to know, in general, we need to know the reduced temperatures and pressures and sometimes the specific volumes. So if we start looking at the initial state on the table, okay, because we know the initial pressure and temperature. So that means we know that the initial reduced temperature and reduced pressure. And the reason we're interested in this is because if we know the initial reduced temperature and pressure, then we could find the initial reduced volume. And of course, the reduced volume times 1.5 is the final reduced volume. And knowing the final reduced volume and the final reduced pressure, which is the same as the initial reduced pressure because it's a piston cylinder, knowing those two bits of information, we can find the final reduced temperature. Of course, reduced temperature, if you multiply it by the critical temperature of the fluid you're working with, you get the actual temperature. So that's going to be the sort of game plan for this. So let's find the initial state reduced temperature. So we start at 300 Kelvin. And for methane, if we look in the tables, we'll find the values we're interested in. So it's 191.1 Kelvin is the critical temperature of methane, and 4.64. 4.64. These are what we're interested in for these two values. Let's go back here. So 191.1. So this is again the reduced temperature at the initial state, and it comes out to 1.57 approximately. And I'll just put a 1 there. PR1 is going to be equal to, again, our actual measured pressure. So 8 megapascals over 4.64, which is the critical pressure. That gives us a value of 1.72. Okay, now we're going to take these two values and we're going to see what this tells us about the specific volume. And we're going to use the specific volume as our link to go from the initial to the final state. The reduced specific volume, I should clarify. So going to the compressibility chart here, let's see, let's draw a line for our reduced pressure, okay, which we know is at 1.72. So that's right around, I guess, there it is. This line, I'm going to try to keep it as neat as possible. Great. Okay, so we're on that straight black line somewhere. Great. Um, and we know that we're going to be at a reduced temperature of 1.57. So if we look between the 1.6 and the 1.5, we're going to be closer to the 6. And we see that gap between these two. So we're probably right around there. And if we follow it back, we get a Z1 of about 0.88. But what's interesting or what's useful for us is that we can read off of this intersection point the reduced specific volume. And the reduced specific volume are these dashed pink lines. So you see here, VR equals 0.2, 0.25, 0.3. It's incrementing by 0.05. But we see that we kind of fall on this line here, this dashed line, which is 0.8. So we can say that VR1 is 0.8, but that gets multiplied by 1.5 when we go to the next state. So VR2, so it's 0.8 times 1.5 is 1.2. Now we know two things. We now know the reduced specific volume at the second state, and we also know the reduced pressure at the second state. And we know the reduced pressure because, like I said, it's the same as the initial reduced pressure, which because it's a piston cylinder, the pressure is constant. So we're staying on this same black vertical line here, but we're going to move to where this crosses the 1.2 specific volume line, right? If you follow it here, you see they cross right around here, okay? Right on this pink line, which is 2. Well, it's a little higher, actually. It crosses more like the 2.1, okay? This line, this solid line, and this hatched line here intersect at about a value of TR is 2.1, so it's a bit more than this. So if we know that TR2 equals 2.1, and we also know that TR is just the real temperature divided by the critical temperature, then we know that TR2 times T critical should give us the temperature that we're looking for. And if we do that, so it's 2.1 times 191.1, which was what we found to be the critical temperature, getting 401.3 Kelvin. So this is the temperature, the final temperature, as predicted using the compressibility chart. So naturally, we expect this one to be slightly more accurate, well, significantly more accurate than using the ideal gas law, because as you can see, our values of reduced temperature and reduced pressure are not that far away from 1. They're not orders of magnitude bigger or smaller. So we wouldn't expect the ideal gas equation to be that accurate. So we got 450 with the ideal gas equation. Now we're getting significantly less. We're getting about 400. So just food for thought, considering the differences between compressibility being factored into the equation versus not factoring it in at all.